Okay, let's see. Oops, sorry. Sorry, I need to stop sharing. Voila. Okay, here we are. And I wanted, now I lost, okay. Voila. Okay, so good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheP. Today, we are very lucky to have Professor Jianshu Cao with us. Professor Cao, let me briefly introduce him to you. He's a professor of chemistry at MIT, but he did his PhD in physics, which is very nice, at Columbia University in 1993. And after a few postdoc stations, he joined MIT as far as 1998. Yeah, he's very well known for his work on quantum dynamics of condensed phase systems and single molecule kinetic. And at the moment, he's working on theoretical and computational models of quantum dynamics, of dissipative quantum dynamics, in particular with the intention of modeling light harvesting system, organic semiconductors, and quantum devices. And the talk this evening will be on this part of his research, but he's also interested in non-equilibrium chemical networks and applications in biophysical systems. Yeah? And Professor Cao is teaching a very nice course in non-equilibrium statistical mechanics of physics. Remember, yeah, that you can watch on the MIT OpenCourseWare website. So if you are interested in non-equilibrium physics, that's the place to go. So, Professor Cao, we are really very happy to have you with us this evening, and that you accepted our invitation. And we are very much looking forward to your presentation. So if you would like to start sharing your screen, you're welcome to start your presentation. And while you do that, I will remind our participants that they are welcome to ask questions using the question and answer facility. And Dr. Sinaisky, who you see at the top of your Zoom window, will coordinate the question and answer sessions. And yeah, so I will leave that part of the talk to him. So, Professor Cao, we are very excited to listen to your talk. So thank you very much. Over to you.
Well, thank you very much, Francesco. It's an honor to give a talk here. And it's also very interesting to give a talk, online talk. And I think it makes the interactions interesting to interact through this way. Thank you very much for the arrangements. Now my talk will be on the stochastic approach. And there are two parts. The first part is numerical. It's a stochastic simulation. It's work mostly done by former postdoc and Jeremy. The second part is on the unified stochastic formalism, and the work done by another former postdoc, Changyu. So as Francesco mentioned, you are welcome to interrupt, ask questions. So to motivate the talk, let me show a few applications. We know that it's important to understand the quantum environment, the open quantum systems for applications to quantum technology. These are some of the examples my group have worked on. The first example is the quantum transport in molecular aggregates. And here, the organic systems is under the influence of the phonons, and the phonon is a bath. The second example is a light harvesting energy transfer in photosynthetic systems and also in dendrimers. And of course, the energy transfer is assisted by the protein environment. We are also interested in quantum thermodynamics. Now, quantum thermodynamics, by definition, involves a thermal environment. And here is a picture of a quantum heat engines. More recently, we are working on the thermalization of strong driven systems in the presence of the bath. And of course, we deal with the Floquet-Gibbs states. So how do we describe dissipation? Well, let's first look at the classical system. We use the example of the Brownian particle. Now, clearly, we can describe the Brownian motion with probability, Pxt. And the probability follows the Fock-Planck equation. And this approach is called deterministic probability approach. Alternatively, we can also describe the Brownian particle with the Langevin equation. In the Langevin equation, on the right-hand side, there's two forces. The F is a stochastic noise. And this term is a friction. So therefore, this is a stochastic equation. And the noise and the friction must obey the fluctuation-dissipation relation, which defines the thermal equilibrium. Now, if we average over the stochastic Brownian motions, we will recover the probability. In other words, the deterministic approach and the stochastic approach are equivalent. Now, what about quantum mechanics? Well, the more popular version approach is deterministic. And here, instead of a probability, we have the density matrix. And the density matrix evolves under this Liouville equation. All the quantum measurement is the expectation value of this measurement of this operator A weighted by the density matrix. There have been many numerical algorithms, as well as the second order quantum mass equations, such as the Redfield equation. And these are the numerical methods, such as hierarchy, MCTDH, MPS, Quabi, etc. Yeah. Alternatively, one can also describe open quantum systems using the stochastic method. And here we have a stochastic Schrödinger equation. So on the top of the time-independent part, we add a stochastic term. And this noise is a quantum noise. And it obeys the fluctuation-dissipation relation. So the correlation function here is complex. And if we average over all the stochastic solutions, we can reproduce the density matrix. There's, however, one difference between quantum and classical. In the stochastic picture, the stochastic wave functions are not physical. But the average, the stochastic average, do produce the physical quantities. But each realization is unphysical. And there also has been various versions of stochastic approach, including quantum state diffusion, stochastic Liouville equation, and stochastic path integrals, etc. So one of the early examples of stochastic approach was a paper I did when I was a postdoc. we simply realize that for the harmonic bass, each harmonic oscillator can be described by a quadratic action. And the quadratic action can be sampled using the Monte Carlo technique. So we sample the harmonic coordinates, and then we propagate the system under a given set of harmonic coordinates. And here we have to take the average. The average is taken according to this cartoon here on the left. So there's actually 3 paths. The initial condition is sampled by the imaginary path integral. Then the initial wave function or initial coordinate is propagated twice. So this is called forward path or backward path. And they're associated with a bread and a cat. And at the end of the propagation, we make a product. And that is the density matrix. And if we average over all the harmonic oscillator configuration, we will produce the density matrix. And here is the result for the spin boson model. The K is the Kondo constant. So clearly, as we increase the Kondo constant, the coherence is suppressed. So this is perhaps one of the first stochastic simulation. So according to this cartoon, there's actually 2 propagations. And this will be the forward and backward propagation. And each of them is described by a stochastic shorting equation. Now we take the product of the bra and the cat. Then we have the stochastic density matrix. The stochastic density matrix obeys the stochastic Liouville equation. So this Liouville equation is simply the combination of 2 stochastic shorting equations. So this was already shown in our paper, but later published by Stockberg and Grabert. So we use this as a starting point. And in the last few years, we have developed a few projects. On the one hand, we use the stochastic equation as a starting point to show that the stochastic picture applies not only to the harmonic bass, but applies to any quantum environment, including boson bass, fermion bass, spin bass, or any anharmonic bass. Then we use the stochastic equation to derive the quantum mass equation, which is a family of hierarchy equations. So this is to show the stochastic approach is general and it is equivalent to quantum mass equation. Also, as a numerical method, we used the stochastic approach to calculate the imaginary time density matrix. And I will introduce this. In addition, we also use the stochastic approach to calculate the spectrum and Forster rate in molecular aggregates. And I will not discuss this part of application. And then we also combined stochastic with deterministic approach to introduce a hybrid method. And now I will introduce the stochastic hierarchy equations. So let me begin with the numerical part. So to motivate the problem, let me ask a simple question. If we have an open system, what will be the non-time limit? Well, the answer is very simple. The non-time limit will be the Boltzmann probability. But it is the Boltzmann over the entire system plus Bass. So this is the entire Hamiltonian. If we only care about the system alone, then we need to trace out the Bass. The result is the thermally reduced density matrix. Now, if the system does not commute with the system-Bass interaction, the reduced density matrix is not the same as the Boltzmann function of a system. So in other words, the reduced density matrix is not canonical. So how do we calculate the reduced density matrix? Well, we can use the Fermion's path integral. The exponential part of the path integral has two terms. The first term is exactly the action of the system without the coupling with the path. The next term describes the influence of the path, and this is known as the Fermion-Vernon influence functional. This functional is non-local in time. Two different times are correlated through this correlation function. And for the harmonic path, the correlation function is completely specified by the spectral density. So all the difficulties of an open quantum system comes from this non-locality in the influence functional. And for this, I'll refer you to the textbook by Francesco. So this is the book for open quantum systems, and you should definitely get a copy. Actually, I have multiple copies. Yeah. So one technique to unravel this non-local correlation is called stochastic unraveling. And based on the Hubbard-Stratonovich transformation, the transformation is rather simple. For example, if we have one dimensional Gaussian function, we can simply express this as the integral with another Gaussian variable, linearly coupled to our coordinate q. So it's a simple Gaussian integral. Now we extend this to n dimensions. And if we take the n to infinite, then we have the functional form. In this functional form, we introduced the auxiliary field, which is a Gaussian variable, Gaussian function. This Gaussian stochastic field coupled to our system linearly. If we integrate out this auxiliary field, we recover the influence function now. But with this auxiliary field, the coupling becomes linear and local. So that is the stochastic unraveling. So in the Fermion-Vernon influence function now, we have a non-local correlation with the introduction of stochastic field. We have only the local coupling. Therefore, we can write down the stochastic Schrödinger equation with the linear coupling to the stochastic noise. And stochastic noise can be sampled using the Monte Carlo technique. So this is one advantage. And in addition, we can deal with any type of the spectral density. And sometimes many techniques, for example, hierarchy, is limited to exponential noise. And the copy is typically limited to relatively short memory time. But this technique can apply to any type of memory. And also because here we use shortening equation. Therefore, we can use wave function instead of density matrix. And the wave function takes much smaller computer space. Therefore, we can deal with a much larger system. So these are the advantages of a stochastic simulation. And here I'm going to present two numerical examples. The first example is the LH2 BA50 ring of the purple bacteria. It's a perfect ring with 16 or 18 identical molecules. Previously, the Jordan's group have calculated the density matrix numerically and propagated for a very long time in order to recover the Boltzmann function. But surprisingly, they do not recover the Boltzmann function, and because it's long time limit, the steady state isotonic population. Of course, now we know this is exactly the thermally reduced density matrix. And here's comparison. The black line is a Boltzmann function. The red line is the reduced density matrix. And even for such a biological molecule embedded in protein and water at room temperature, the difference in population can be as large as 20%. So quantum effects can appear even in biological molecules. And with the density matrix, we can also calculate the localization length. Without coupling with the phonons, without disorder, the wave function will spread over the entire ring. But now, because of the coupling with the bash, which is the Polaron effects, the size of the wave function will shrink. And this is measured by localization length. And here, the size decreases with the temperature. In addition to the change in the population, the basis set will also rotate because of the coupling with the thermal bath. So the thermalization rotated the basis. As a result, the reduced density matrix is no longer diagonal in the isotonic eigenbasis. And this rotation can easily be described for spin on the Bloch sphere. On the Bloch sphere, we have two vectors. The one vector is the eigenbasis associated with the system Hamiltonian. The other vector is associated with the reduced density matrix. And the theta is the deviation angle, which essentially describes the rotation of the basis set. So now we use the stochastic method to calculate the deviation angle. And here the lambda is the reorganization energy. It's a measure of a system bash coupling strength. So as we increase the lambda, the deviation becomes larger and larger. And this, of course, is expected. Essentially, the basis set rotate from the eigenbasis to the molecular site basis. The lower panel is more interesting. Here, we take extremely small coupling. So at a high temperature, we recover exactly the Boltzmann function, because the canonical Boltzmann function is achieved by weak perturbation of system. But as we decrease the temperature, suddenly there's a dramatic deviation from the Boltzmann function. And this indicates the breakdown of the canonical probability. And of course, this is a purely quantum mechanical effects. So far, we've been talking about thermal distribution, which is associated with the imaginary time path integrals. What about real time? Well, as I mentioned earlier, back in 1994, we published one of the first stochastic simulations. But what we found at the time is that if we continue the simulation to the longer time, it becomes harder and harder to converge. The reason also rather simple. The quantum noise is a complex noise. If you add a complex force to the Schrödinger equation, then the wave function, the amplitude of the wave function can grow exponentially. Since, as we mentioned earlier, the wave function, stochastic wave function, is unphysical. Therefore, it's not necessarily normalized. As a result, it becomes harder to converge at a longer time. And the same issue also appears in other stochastic methods. So recently, we come back to this problem and proposed a new technique called hybrid approach, which is to combine stochastic with deterministic. So I'll talk about this method. In addition, we can also take advantage of the short time without going to the longer time. For certain quantities, such as a spectrum, emission absorption spectrum, the short time will be sufficient. And also rate, like forced rate in molecular aggregates. We also developed a technique called transfer tensor method, which allows us to take the short time dynamics and extrapolate to longer time. So therefore, we can combine the transfer tensor method with stochastic simulations. For this talk, I'll introduce the hybrid approach. So here again is the Feynman's path integral in real time. And the inference function now here has two terms. The real part and the imaginary part. The real part is associated with the quantum fluctuations. And this part is highly non-Markovian. And the memory time increases as the temperature decreases. And that's the reason that most quantum mass equations will fail at a low temperature because of this non-memory time. But the stochastic simulation works perfectly for the fluctuation. The second term is the imaginary part, and the imaginary part is responsible for quantum dissipation. And this part, as I mentioned earlier, is responsible for the divergence in the stochastic simulation. But interestingly, for the bosonic bath, the imaginary part is actually independent of temperature. Therefore, we can use the deterministic approach to deal with the imaginary part. And this suggests us to use a reference system. So we partition the real correlation functions with the help of the reference. Then we apply the quantum mass equation to calculate the reference system. The reference system is defined at higher temperature. Therefore, it does not have the quantum correlation. And standard quantum mass equation will work perfectly. And this takes care of the imaginary part. Then the real part is counted by stochastic sampling. So in other words, on the top of a standard quantum mass equation, we add a stochastic layer. And this allows to combine the advantage of the stochastic and the deterministic approach. So we take the advantage of two approaches and combine them. And with this algorithm, we're able to simulate extremely low temperature and strong system bash coupling. And here I'll present two numerical examples. The first example is the energy transfer between donor and acceptor. Usually, we use the forced theory. Forced theory is a special case of the Fermi golden rule rate. And indeed, the red line is the forced rate. The black line is the hybrid simulation. And indeed, they agree quite well at high temperature. But then at the low temperature, there's a systematic deviation. And this deviation persists even towards zero temperature. So this is a purely quantum effects. It's a quantum nuclear effects. And it's still there even towards low temperature. Yeah. Therefore, we need corrections to forced theory. The next example is about the system bath entanglement. And here we consider the two-qubit system. And we calculate the concurrence. Previously, there's a hierarchy calculation, which will show that the entanglement first decays, and then it comes back. And this recurrence is a feature, is a signature of the memory effect of the bath. But the simulation truncates at about lambda equal to 1. That's about how far one can go with a standard simulation. Now with a combined stochastic and hierarchy method, we're able to push the lambda to 10 times larger, lambda to 10. As a result, the recurrence is completely killed. The entanglement decays monotonically to 0. So this is an extremely strong coupling effect. And with a standard technique, we'll not be able to observe this effect. Okay. So now I'm done with the numerical part, and the second half, which is a shorter half, will be on formalism. And as I mentioned earlier, it has two steps. The first step, we want to establish the generality of the stochastic equation. It applies not only to the harmonic environment, but also apply to fermion baths, spin baths, or any baths. Secondly, we want to use the stochastic equation to derive the quantum mass equation, which in this case will be a family of hierarchy equations. To start, we again have a general form of the system-bath interaction. And here we have the bath is general. The specific bath can be described by the properties of the bath operator. For Boson baths, the operators are based the commutation relation. For fermion baths, the bath operators are based entire commutation. For spin baths, of course, the operators are based the spin algebra. Now, as I mentioned earlier, all the difficulties come from the system-bath coupling. And again, we can use the stochastic unraveling. So for any bilinear coupling, we can introduce a white noise, which will couple to the two components, A and B, separately. Then, by stochastic average of this white noise, we can reproduce the bilinear coupling. So with this trick, we are able to decouple the system and the bath. So now we have two separate equations, one for system, one for bath. They are completely independent. And here there's two different noise, W and V. And these are two noise associated with the forward path and backward path. To connect to any physical measurements, we have to take two averages. The first we average over the bath degree freedom. As a result, we obtain the stochastic density matrix. Then we average of stochastic noise. The result is the reduced density matrix. That is a density matrix for the quantum mass equations. And this is a physical quantity. So now we're going to do this step by step. First, we need to solve the bath degree freedom. And that's the solution. It actually looks very similar to the inference functional. And again, here, there's two noise, forward and backward path. The B is a stochastic field, which is very similar to the auxiliary field in the Hubbard-Stratonovich Transformation. But this is more general because it is not limited to Gaussian bosonic baths. In fact, here we have not specified the bath yet. So all the features of a bath is encoded in the statistics and the correlations of the stochastic field. And then we multiply this trace to the system density matrix. The result is the stochastic density matrix. The stochastic density matrix obeys the stochastic equation. And this indeed is the most general version of a stochastic Liouvillean equation. And all the properties of various kind of quantum environment is now coded in the details of noise. In other words, the stochastic equation will be same, but the noise will be different. For example, for bosonic baths, we'll use the complex Gaussian noise. And this noise is completely specified by two-time correlation function. And there's actually three types of correlations. The correlation among the forward paths, the correlation among the backward paths, and correlation between forward and backward. So this version for the bosonic baths is the traditional stochastic Liouvillean equation. Now we can also extend this to fermionic baths. For fermionic baths, we're going to use the Grassmann noise. As a result, we need to keep track of the order of the noise, as well as the sign convention. Because it is a Gaussian, and we only need the two-time correlations. The two-time correlation for fermionic baths has order symmetry with a time reversal. And this, of course, is to obey the Fermi-Dirac statistics. Furthermore, we can go beyond the Gaussian noise to have non-Gaussian effects. And one way to do this is to introduce multiple time correlations. So in addition to two-time correlation, we have a set of four-time correlations. And this can go even to higher orders. In this way, we can completely capture the non-Gaussian statistics. So far, we have established the general version of the stochastic Liouvillean equation. Do I have a question?
Ilya, would you like other questions for Professor Cao?
No, there are so far no questions. There is only your comment that you ask people to ask questions in Q&A facility.
Thank you.
Sorry, I didn't hear clearly.
Sorry, no questions yet. No questions yet.
Okay, good, thank you. All right, the next step is to use this version of stochastic equation to derive the quantum mass equation. In this way, we can show the equivalence between the stochastic approach and deterministic approach, and also to obtain the generalized version of the quantum mass equations. And the technique, of course, is rather, as I mentioned earlier, is to take this stochastic density matrix and take the average, stochastic average. Then the result is the reduced density matrix. And this is a formal expression. And this is the bar is the average of stochastic noise. And clearly, the masked equation for the density matrix is coupled to this term. Now, this term is actually the first moment of a stochastic field. Therefore, we can introduce a family of auxiliary density matrices, which is essentially the moments of the stochastic field. So the zeroth moment will be the standard density matrix. And the first density matrix is the first moment, and the second type will be the second moment, etc. So therefore, from this masked equation for the reduced density matrix, we can see that the row 0 density matrix is coupled to row 1. And in order to solve row 1, we need to derive the masked equation for row 1. And that masked equation will couple to row 2. And then row 2 is coupled to row 3. As a result, we have a tree of a hierarchy equations. So this is a general form, and we have not specified the base yet. And to do this, we're going to project this formal masked equation to a basis set, to a basis function. So here we introduce a complete orthonormal function basis phi, and then expand the correlation function in this basis. Similarly, we can also decompose the stochastic field in the same basis. As a result, we have a set of stochastic functions. Then the auxiliary field, auxiliary density matrix, is simply defined as the moments of this set of stochastic functions. And this allows us to explicitly write out the hierarchy equations. So this is a hierarchy equation for bosons. And you can clearly see the tiers. So the nth tier is coupled to n plus 1 and minus 1, and also all the other tiers. Interestingly, if we choose the exponential noise, the last term will vanish, and that will recover the standard hierarchy equation. But this is an extended version. In fact, we have used stochastic version to calculate the quantum phase transition in the spin boson model. This is work by my former student, Jianan, who now a professor in China. And we can also derive the quantum masked equation for fermions. In comparison with the bosons, there's two differences. The first difference is a sign. So there's a minus sign, and this is to impose the anti-commutation for the fermionic operators. Second is this 1 minus n times n. That will restrict the choice of the integer, the tier, to 1 and 0. Of course, this is due to the Pauli exclusive principle. And this is the hierarchy equation for fermionic baths, and that has been previous work. And this version is more general because it is not limited to exponential noise. One interesting application is to use fermions to describe spin bands. So why do we care about spin bands? Well, there's many quantum devices are based on the spin systems. And this device is important for quantum computing and quantum sensing. And a common issue about device is dephasing. And dephasing is caused by the coupling to the spin environment. Therefore, it's important to simulate the spin. And here we developed two approaches. The first approach is to map the spin operator to a pair of fermionic operators. And C and D are fermion operators. The C fermions can transform the spin into fermions. It's similar to Jordan-Wigner transformation. The D fermions account for the sign with multiple spin flips. And now we are able to map the spin bands into two fermionic bands. Now the question is how to simulate, how to solve two fermion bands. Well, here is a general strategy. We again use a stochastic unraveling to decouple the bilinear coupling between the C fermion and D fermion. Then we trace out the D fermion to obtain a stochastic equation for both the central spin and C fermions. And finally, we derive the hierarchy equations for the central spin. And here is a numerical result. So we take this central spin model and calculate the off-diagonal density matrix element, the coherence. And here are the different tiers of hierarchy. So clearly, about 20 tiers, we are able to achieve convergence. For this simple problem, we actually have the exact solution. The other technique, the other approach to calculate spin bands is to map spin to a general anharmonic path. For example, here is the Morse oscillator. Morse oscillator has a finite number of bounded states. And if the anharmonicity is sufficiently large, we can have only two bound states. Then two bound states can be mapped to spin. So therefore, we can use our generalized hierarchy equations for anharmonic system to systematically calculate the spin environment. And here is the hierarchy equation for spin. I won't go through this, it's rather complicated. And again, we use the same model. So this is the exact solution. And if we take the Gaussian approximation and truncate the correlation to second order, it will be the blue line. And if we go to the next order, the fourth order, the agreement is much more improved. That's the black line. And we can, of course, systematically include 6-point correlations, 8-point correlations, etc. Okay, so essentially all the results, essentially all the formal equations or formalisms are presented in these two papers. So I think I should summarize. So we discussed a stochastic method to predict the deviation from Boltzmann, and we proposed a stochastic deterministic approach for the low temperature strong coupling. And we formulated a unified stochastic equation. and use it to derive a family of hierarchy equations. With this, I'd like to thank again two postdocs, Changyu, Jeremy, and NS funding. Well, thank you. I'd be happy to answer any questions.
Thank you very much, Professor Cao, for this really great talk on this very powerful stochastic simulation method. So thank you so much.
Well, thank you.
Yeah, no, absolute pleasure. Thank you very much. Ilya, are there questions for Professor Cao? Or since we are not so many, maybe we can ask participants to raise their hand and they might be willing to pose the question on their own.
So far, we don't have yet questions, but maybe while people are thinking, I can ask my question.
Please go ahead.
Sorry. My question is, what is the kind of computation? Is there any difference in computational requirements? For example, if I compare similar spectral densities of, I don't know, spin bars and the bosonic bars, would it take the similar computational resources, or there will be some differences?
Well, when we, that's a good question. So, in fact, in this expansion, to second order, the spin bass is actually can be mapped to bosonic bass, but with a different correlation function. I think you also know this because you have some paper on the spin bass. This actually is equivalent. But of course, because the spin bass is intrinsically anharmonic, therefore we have to go to high orders. And as a result, the numerical expense is larger for the spin bass than for the bosonic bass.
Okay, so if I would like to describe, I don't know, some sort of like interaction of some system with a spin glass, it will be much more computationally intensive than with a similar bosonic bar.
That's right. Yes, it is it's more expensive than bosonic bass with a similar temperature and similar spectral density.
Okay.
Or another way to see this is that the spin bass is actually, as we mentioned earlier, is actually equivalent to two fermionic bass. Therefore, the hierarchy equation has two layers associated with the two bass. That's also the reason for the expense, the difficulties of the spin bass.
Okay, thank you.
And if I can also ask a question, just out of curiosity, from a very practical point of view, for instance, if you simulate a biophysical photosynthetic setup, what hardware do you need to run the simulations?
I'm sorry, what?
No, what hardware do you need? Can you run the code, for instance, on your laptop, or you need
so the calculation we have done actually relatively simple. So essentially, in this paper, in these two papers, all the calculations was done on the laptop.
Okay, very good. Yeah. Thank you. That was just a curiosity. Yeah.
But as you mentioned, you are correct. For complex Liouville systems, such as LH2, then we have to use maybe supercomputer or clusters to do that.
Thank you.
Okay. Camille have a question, but I allow him to talk. He can unmute himself and ask his question.
Okay, hello. Thank you for this interesting talk. I have in fact, I had two questions. So maybe the first one is, so you mentioned briefly in the beginning, you talked about Floquet basis or Floquet technique. And yeah, I was just wondering if these techniques that you present are also applicable for driven dissipative system, which are becoming very studied.
Yes, definitely. Yes, because we can also introduce time dependence in the system part of a Hamiltonian. And then we can describe the driven system. And in fact, we already used the Mars equation to simulate the driven spin boson model.
Because yeah, as far as I understand, when you use like the Floquet basis to describe your driven dissipative system, you end up having a situation as if you had like an infinite number of baths. I mean, it depends also on the kind of driving, but if you take a general situation, the dissipation happens as if you were, at least from the point of view of the mathematical description, as if you had like an infinite number of baths. And so I just thought maybe this might be problematic if you want to apply this technique.
Yeah, so that's a very good point. So actually in this paper, we actually used the hierarchy quantum mass equation to simulate a driven and dissipative two-level system, a driven spin boson model. And in the simulation, we actually don't use the Floquet basis. We simply add the time dependence to the system part of the Hamiltonian and numerically propagate the quantum mass equation. So that's a numerical approach. Of course, for the theoretical analysis, we do use the Floquet basis. So in this paper, we have both theory and numerical. The numerical part is done purely, completely with quantum mass equations without the Floquet basis.
Okay, thank you. And yeah, my other question is, you mentioned one or even two times that the stochastic wave function is not physical, and yes. So I was a bit confused because at least from my idea or my point of view, I thought that like the stochastic wave function like represented like each how can I say, realization of the dynamic. So like you start with your system in a given state, and then yeah, the stochastic wave function will somehow represent the realization of one trajectory. And so now if you said it's not physical, it means that my interpretation is not anymore valid, maybe.
Yeah, so that's a good question. In a stochastic equation, the stochastic force is a quantum noise. The quantum noise is complex. Therefore, this stochastic Hamiltonian is not Hermitian. And the non-Hermitian operator, the wave function cannot represent a physical quantity. There's one special case, that is this noise is a classical noise that is associated with weak measurements. Then the wave function is well defined.
Okay, so this view that the stochastic wave function somehow represent each realization of the dynamic, it's not a very good view. Well, or at least maybe one should be careful with this analogy, maybe.
Yes, you're absolutely right. But of course, if the force is a classical force, classical noise, then we can interpret each realization as a physical measurements.
Okay.
But in the numerical, in this exact representation, the force is not real. It's a quantum force.
Mm-hmm.
Then the wave function, the stochastic wave function, is unphysical.
Okay.
Now, Camille,
Okay,
I think
thank you.
What you have in mind, Camille, is the quantum optical situation where in the case of continuous measurement, you have this measurement interpretation of the wave function. But that's
Yes, something like that, yes.
Just a specific case, not the general one. Yeah.
Mm-hmm. Yeah. Okay, thank you.
You're welcome.
Ilya, are there more questions?
As far as I could see, there is no more questions.
Okay, then if there are no urgent questions, considering also the time, Professor Cao, just then I only have to thank you again very, very much for an excellent talk on these very powerful methods that that probably have a very bright future and lots of applications still ahead. So thank you very much again for
thank you very much
to coming to Zoom this evening to give us the talk, and we will stay in touch. And I hope that soon there will be an opportunity to meet in person on some continent. Yeah.
Yeah,
so
certainly. Thank you very much.
Thank you very much again, and thank you also to all the participants for joining us regularly in this colloquium. So thank you very much again, and have a good evening to the locals and a good day to you.
Yeah. Good night, everyone.
In Boston. Thank you very much. Goodbye.
Thank you. Bye-bye.
Bye. Bye. Cheers.
Bye-bye.